Hi, our project is a driverless system that warns the drivers when it detects their eye closure to prevent the accident while they're driving. The system uses a camera and an ML model implemented on Raspberry Pi. We wanted to improve the road safety by offering affordable and offline solution for everyday drivers. And this is our requirement document, but it's too long to review in detail. So we're going through it and discuss some important key points from the document.
So for the design and computation constraints, so for the computation constraints, the Raspberry Pi isn't very powerful, so we need to make the model and the code efficient and to keep running smoothly in our real time without delay. For the changing in lighting conditions, so as we know, inside the vehicle, the lighting can change a lot, so the system need to work well in all the kind of lightings. So for the privacy and data security. To protect privacy, the system processes the data instantly without saving or sending the pictures or the video, ensuring sensitive information and to stay private.
And now let's have a look at the system features. So we have two main system feature here, which you can see on the screen. The first one is a real-time eye detection for the closure, and also we have the driver alert. So the first one, the real-time detection for the closure. Our main idea is to detect if the driver is falling asleep using a machine learning model and camera to detect if the eyes are closing. So this is one of the main feature we have to implement, and it need to work in real-time system because it need to provide a feedback in real time without any delay. So this is why it's one of the main system feature we have, and we have some like functional requirements for that, of course, which is like need to run without any delay, real time, and need to work on the Raspberry Pi since it's a ARM machine, not AMD. So the model need to work there, and also it should be accurate enough. For example, if the person is blinking, it should not give it a false positive as a sleepy, and it need to work offline. So for the driver, for the alert system, also again, so we are trying to have a speaker which only will give either a buzz or like a recorded message to display to the user as a feedback if he's falling asleep to wake him up or alert him. So that's the second main feature. So it need to work also with the project and with the Raspberry Pi, and it should be the goal for it is to provide a feedback alert the driver. And after the two main point of the feature we have, let's move to the data requirements.
So for the data, we use the dataset from the Kaggle, which is open to public. The dataset is consistent of only of the eye images, not entire face, because for the model, processing just eye images is much simpler and faster. So it means the model is able to focus on detecting driver's eyes only. We made the data into two different classes, which has 2,000 photos of closed eyes and 2,000 photos of open eyes. And this is an example of the image we used to train our model.
Okay, and now let's move to the interface requirements, which is at the bottom here.
So for the interface requirements, we have user interface, which is made of like power conditions where the user has to use a step down converter to convert from the power source from the vehicle. As we know, it's 12 volt, and the Raspberry Pi will have to take 5 volt power. So we need to use the step down converter, and the user will have a switch or a button for the driver to indicate to turn on the Raspberry Pi, turn on the system if he wants it to be working or not. A speaker alert, which is a user do not interact too much with it. Is this the speaker sends a voice that alerts the driver in case of drowsiness detection, and the camera position where the user does not interact with it, it just has to face the driver's face where it can see clearly the eyes. And for the hardware interface, So we have the same kind of interface where we have the power resource where we need to use a step down converter, as we said, for from the vehicle port, which is 12 volt to the Raspberry Pi to make it 5 volt. And for the camera, so we have two different type of camera options that we're using. A Raspberry Pi camera Model 3 connected to a VSI camera serial interface, or we're using simple USB connection that camera which can connect to any laptop. And for the speaker, we are using a speaker called mini external USB serial speaker connected directly to the Raspberry Pi by USB, and also the button or switch uses a physical GPIO connected into the Raspberry Pi.
And now for the software interfaces, so the Raspberry Pi which we have, it have an operating system which is the default Raspberry Pi OS, which is the default one from the Raspberry Pi official website. And the main language we're using in our project is the Python. We use the Python for training the model. The training the model happened on Google Colab. And then we use the Python again in the IDE, which is called ByteCharm, to take the video from the user or like from the camera, process them as frames, and then send them to compare them to the model to find the result. So there's some libraries here listed which we used, and after this there is a lot of information in this document. We're not going to go through all of it, so we'll leave that for, we have a link for it for anyone to go and read it. But now let's move to the next part, which is the proof of concept and prototype.
So we found that our project is doable through the proof of a concept, and then we wanted to provide a prototype demonstrating how the system functions actually. We are able to demonstrate it. The model runs on our computer and our Raspberry Pi, and we confirm that our project can operate in a real time on a microcontroller. So now we're about to share our demo videos, and we hope this helps you better understand how the project works.
Okay, so we'll start with the video of the project running on the laptop itself. And let's see that here. Let's check the quality. It's very bad. Let's wait for it, or let's reload it. So we can see that he's trying to move around, and it says in the corner open or close when he flash, and if he stayed for more than 2 seconds it will start giving like a sound beeping. And as I said, this video, like this model running now, not on the Raspberry Pi, on the device itself. And now if we move to the next one, which is the other video is running on the Raspberry Pi itself. So after a few trials and like changing and adding and modifying the code, we had to convert the model to TensorFlow Lite because it doesn't work with the TensorFlow only on the Raspberry Pi. And after we did that, we ran a test to see, and this is the result on the Raspberry Pi. The only thing it doesn't have in this video is the alert system, which we didn't implement, but it still show you that if it's open or closed or blinking. So you can see in the corner also, it says either open or closed based if I'm blinking or not. And if I stay for long, another line came just in underneath. I'll repeat it here again so you can see it. Or maybe I have to stop it when it says. So after 2 seconds, and let's wait until I close. Yeah, well, okay, it's too hard to stop it, but you can see that another line came underneath saying that sleep is detected, and that happened after 2 seconds of closing. And when I open my eyes, this is why it disappeared very quick. And now we are testing also in night light. So you can see we turned the light off, and we still were able to get good detection and I'm very sure it's a matter of which type of camera you're using, because the laptop camera was not able to detect this. So after this now, we finish this, we move to the testing.
So for the testing, we have we are be using user testing, which is more appropriate for us as it's our primary goal is to validate the end user's experience with the eye detection functionality. Unit testing, it's less critical for us, but we did unit testing in for our projects where we tested the speaker on itself with a Raspberry Pi, the camera on itself working with the Raspberry Pi, the model itself. We tested it like on our computer, like without uploading it to the Raspberry Pi. We tested and then the model itself on the Raspberry Pi, and now we're just gonna combine everything and test it for the user testing. So for the testing scenarios we'll be doing, so testing the live eye detection accuracy and the performance of the Raspberry Pi, where we'll be testing like the various distance like from the camera, where the user is sitting far away, close to the camera or close to the camera. Testing under different lighting conditions, as we saw in the video. Testing with people that are wearing glasses or without glasses. Testing when driving, looking away or down, or testing the testing the model with multiple faces in the camera where you have a passengers with you in the vehicle. So for the testing cases and testing for the test case results that we have, so for the eye detection accuracy, we we try to validate that the model is correctly identified that the eye is closed or open. So we observe the output on the screen as you saw in the video, like when you're closing your eyes, it will say close eyes when you open. And so we expected it to work fine and correct without any issues, and as we saw in the video, like we had a pretty good accuracy. So the performance of the Raspberry Pi, so the performance of the Raspberry Pi is just ensuring that it's working like very good without delaying or having any delay issues. So we ran the eye detection RPI.pi for 10 minutes and observed if we have any lags. As we know, sometimes you'll be driving for longer time. So we expected it to work without delay, and it did actually work very well without delaying or having any issues. So we tested also different distance, where we tested the distance where the person's sitting close to the camera, or certain averagely kind of far, or like certain a little far. So the steps that we did, we tested like from 25 centimeters away to 2 meters away from the camera. So we expected that the eye be detected correctly even in far distance. So for what actually happened, it was working well with close and average distance, but when it's the camera is a little far away, like we will have less accuracy. So and for the different lighting conditions, so we tested with different lighting conditions where it's nighttime, daytime, and we tested with the natural light as well. So we tested with different type of lighting. So we expect it to work very well with all different type of lighting. So in our case with the computer camera, so when it's dark, it wasn't detecting it correctly. But with the Raspberry Pi camera, it was working kind of good, as we saw in the video. It was working accurately with no issues. So testing it with like people that are wearing glasses, it didn't give us any issues. We tested it with different type of glasses, different shape of glasses. Like we didn't have any issues with it. With multiple faces, like when you have multiple people in the screen with you, where like for example, if you have a passenger, we didn't have any issues, as it only looks at the drivers once it locks on the driver's position, like it doesn't move away to a different face. So for the looking down or looking away, looking around, like around for your surroundings. So we find out when you're looking like down, like the camera will give you closed eye, even though your eyes open. That's because like the camera can foresee it as when you're looking down as you're closing your eyes. It doesn't detect it very well. So for the defects and the plans to improve, for the low accuracy for the far distance, so the eye so it becomes less accurate we move far away. So for our condition is not going to be a big issue, as a driver has to really like sit close to the steering wheel to drive the vehicle, so they cannot be 2 meters away from the steering wheel. And we're planning to put the camera right like by the steering wheel, like on the dashboard, so that shouldn't be a big issue. For the lighting conditions, as we saw, like with the computer camera, will have some flaws, but with the Raspberry Pi camera, it works accurately with no issues. And in the vehicle, we're not going to be using computer camera, so we're going to be using the Raspberry Pi, which is will not have an issue with it. And for the looking around for your around on your surroundings, or looking down, that's something that we need to look farther into it, like this coming semester.
So before I move back to the code folder, I just want to mention one thing, that when we say like the result were well for one of the tests, we don't mean it was like 100% correct. We probably have some like mistakes here and there, but as a general, we're looking at the majority of the cases, and it was working well. Another thing I want to mention, that our major fear from the beginning of this project when we started was not able to deploy the model on the Raspberry Pi, because the Raspberry Pi might not support it. And even if we are able to deploy it, our fear also was not the Raspberry Pi will not be able to process the model and provide feedback at the same time in real time. And we are happy that we were able to deploy it on the Raspberry Pi and get fast feedback without any delay in real time. And this is good because now even if we have to like improve the model, or like let's say add something, then we know that okay, our idea is working, Raspberry Pi is able to do it, we can improve the model and then go back and check it again. Okay, so that was good. Now let's go and see our files here. So we have code folders here. Okay, we have 2 folders inside it, one of them for laptop machine and one of them for the Raspberry Pi. First one, I'm not going to go through all of them, but I want to just mention what are they. So the first one, Capstone here, this is whatever we did on the Google Colab to train the model. So if you open it, you will see the code we did and everything we did on Google Colab until we got the first model which we run on this laptop. And then because we need to transfer it to or convert it to TensorFlow Lite, this is the second code. This file here only has taking the model from here, loading the model from here, and then converting it to TensorFlow and downloading it again. So this file allowed us to have the TensorFlow. Now this file here, which is this one, it's just the code that will capture the eye, the face, and then it will compare it to the model, not to the TensorFlow model, because this is on the laptop, to the model which we did. Okay, and this is the entire code. Just capture the eye, get the eye through the box, which is this one, and then brokers the model, brokers the eye for the image of the eye before we push it to the model, so the input is matching wherever we trained at the beginning. And then here, this is the dimension of the eye, which you see here, these boxes using a face mesh from MediaByte. We're getting the eye, capturing it, but the result which we are getting is not related to any library. We are getting it directly from the predict here. So we are doing it through the model. We are capturing the eye using the face mesh, but we are not using the face mesh to give us any answer, is it closed or open. We're using the model to predict and then give an answer. Okay, and if we go back now here, so this is what this file is. If we go back to the other code, which is the Raspberry Pi, the first one is the setup. Now it took us a few files to keep saving commands, and then when it doesn't work, we redo everything. But this is just the final version, which is only around like 23 commands. This is the steps we take before we run any code, like just to set up the dependencies, check the speaker, check the camera, update the Raspberry Pi at the top here, and then at the end, we create our own environment, we download all the dependencies, and then we run the program at the last 2 lines. So this is just the setup file. And this is the file which is same to this one which we see here, like which I showed you guys, but the only difference that here it doesn't use the actual TensorFlow model which we downloaded, it used the TensorFlow Lite over here. So it's a little different, the procedure is a little different, but the majority of the code, like the functions, we have to progress the image of the eye and get the box around the eye, is basically same. So the majority of this code is same, beside the thing which doesn't work on the Raspberry Pi. We have to change it and make it work. So basically that's everything we have, and we are very excited to continue improving our project and arrive to the final result. Thank you so much for listening.
Thank you.
Thank you very much.